This video explores the topic of energy harvesting within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Today, many electronic devices are portable and battery-powered, including sensor nodes in wireless sensor networks and IoT systems, and wearable electronics like watches, glasses, or clothing. These devices share a common limitation: batteries eventually run out. Lifetime depends on energy consumption and battery type, ranging from weeks to years. Techniques like sleep modes can extend battery life, but replacing batteries is often impractical or expensive, especially for wireless sensor networks with thousands of devices in remote locations. A promising solution is energy harvesting, which represents the process of collecting ambient energy such as sunlight, wind, heat, vibrations, or electromagnetic waves energy and convert it into electrical power to self-power measurement and electronic systems. Large-scale solar panels and wind turbines have long done this, but powering small electronic devices requires microscale energy harvesters, just a few centimeters in size. While they produce small amounts of power, it is enough for low-power electronics like sensors. Microscale systems face unique challenges, requiring innovative designs. Until recently, ambient energy harvesting at the microscale was limited by high power consumption of electronics. Advances in transistor miniaturization and lower supply voltages have dramatically reduced energy use, with power consumption decreasing faster than device size, following a cubic scaling law. Meanwhile, battery technology has lagged behind electronics. Since 1990, storage capacity has grown over 1,000 times, but battery capacity has only tripled. In small devices, batteries take up much of the size and weight, and their slow improvement increasingly limits system design. New storage solutions, like thin-film lithium batteries, fuel cells, or supercapacitors, offer higher energy density but face cost and manufacturing challenges. This figure shows different types of ambient energy available for harvesting. Table 1 lists their power densities, with solar energy being the highest. Hybrid systems can also combine multiple harvesting techniques simultaneously. The architecture of a sensor node capable of harvesting energy consists of the two main parts. The first part is energy harvesting part, which consists of the following components. Energy harvesting unit that collects energy from the environment and converts it into electrical energy to power the node. Power management unit that determines whether the harvested energy should be stored for later use or immediately supplied to other system components. Energy storage unit, typically a rechargeable battery or a supercapacitor, used to accumulate energy for later use. There is also a DC to DC or AC to DC converter, which is needed to provide an appropriate DC voltage for charging supercapacitors or batteries. Photovoltaic cells and thermoelectric generators produce DC voltage, but this voltage is typically very low, so DC to DC conversion is necessary to step it up to a level suitable for charging capacitors. In contrast, converters based on vibrations, electromagnetic RF waves, or wind turbines produce AC voltage, which must first be rectified into DC before it can be used. The second part of the system is a sensing part, which consists of sensors, a microcontroller, an analog to digital converter for digitizing sensor signals, a memory unit for storing the acquired measurement data, and a transceiver for wireless communication. These components from the sensing part are identical to those used in conventional sensor nodes. The energy harvested from the environment is inherently variable. Solar and thermal energy are abundant during the day and under clear weather but decrease at night or in cloudy conditions, while wind energy depends on fluctuating wind speeds. As a result, harvested energy may exceed a sensor node's needs at times or be insufficient at others, making energy storage essential to accumulate surplus energy and supply it when needed. Energy storage and energy harvesting systems can be implemented with rechargeable batteries or supercapacitors. When evaluating storage devices, two key parameters must be considered: energy density and power density. Energy density defines the total amount of energy that can be stored, while power density determines rate of energy delivery, enabling peak or burst power. High energy density supports long-duration operation, such as long driving distance of electric vehicles or extended battery life of smartphones, while high power density enables rapid energy delivery, which is important for vehicle acceleration, power tools, and high-speed wireless communication. Ideally, both should be high, but at present there are no storage systems that simultaneously exhibit very high energy and power density. The two classical energy storage devices are batteries and capacitors. Batteries store energy via electrochemical reactions, offering high energy density but low power density, with slower charging. Capacitors store energy in the electric field formed between their electrodes. Classical capacitors have high power density but very low energy density, making them unsuitable for practical energy storage. A supercapacitor is a capacitor with a very large capacitance, on the order of 1 farad, which is much higher compared to pico or nanofarad range of classical capacitors. In terms of characteristics, supercapacitors lie between batteries and classical capacitors. They have significantly higher energy density than classical capacitors, though lower than batteries, and much higher power density than batteries, enabling fast charge and discharge. Research focuses on increasing their energy density. Supercapacitors offer several advantages over rechargeable batteries. They can endure almost unlimited charge-discharge cycles, while batteries typically last fewer than 1,000 cycles. Their charging and discharging circuits are simpler, and they do not require complex protection against overcharging or deep discharge. Additionally, supercapacitors are more environmentally friendly than batteries. Both supercapacitors and batteries suffer from self-discharge, an undesirable phenomenon in which stored energy is gradually lost over time. Hybrid energy storage systems combining batteries and supercapacitors are also used. There are three main types of supercapacitors: electric double-layer capacitors, pseudocapacitors, and hybrid supercapacitors. The main design goal is to maximize capacitance, which can be achieved by increasing surface area or reducing electrode separation. Supercapacitors exploit both mechanisms. In an electric double-layer capacitor, both electrodes are coated with highly porous materials such as activated carbon, carbon nanosheets, carbon nanotubes, or graphene, and separated by a liquid electrolyte with positive and negative ions. There are two key factors for achieving very high capacitance values. The first key factor is porosity of the electrodes, which allows ions from the electrolyte to penetrate deep into the material, dramatically increasing the effective surface area. Matching pore size to ion size is critical. The second key factor is formation of an electric double layer on each electrode when a voltage is applied, by accumulating of ions from the electrolyte at electrodes. Energy is stored in the electric field between the electrode surface and the oppositely charged ions, which are placed at very small separation distance. The small separation distance combined with the large surface area results in extremely high capacitance and energy storage capability. Discharging is fast and simple. Ions detach from the electrodes and return to the electrolyte, allowing very high discharge rates. Table 2 compares the performance of various battery types, while Table 3 compares batteries with supercapacitors. The figure illustrates how energy available to sensor nodes evolves over time. A battery initially supplies more energy, which gradually decreases until depletion, whereas energy harvested from the environment starts lower but fluctuates and can be continuously used for a much longer period, well beyond the lifetime of a conventional battery. This section covers devices that convert light energy from the sun or artificial sources into electricity, known as solar energy harvesting. Large-scale power generation uses solar panels, while small-scale applications, like miniature sensor nodes, rely on small photovoltaic cells for micro-scale energy harvesting. A photovoltaic cell is essentially a semiconductor diode with an extended p-n junction. When N-type and P-type semiconductors form a p-n junction, electrons and holes diffuse across the junction, creating a built-in electric field that opposes further diffusion. The P side acts as the diode's positive terminal and the N side as the negative terminal. When illuminated, the p-n junction functions as a photodiode. Photons excite electrons from the valence to the conduction band, forming electron-hole pairs. The built-in electric field of the p-n junction drives minority carriers across the junction. Electrons move from the P side to the N side, and holes from the N side to the P side. This generates a photocurrent, which flows opposite to the conventional forward current of the diode. The figure shows the current voltage characteristics of a photovoltaic diode under dark and illuminated conditions. Two key parameters describe photovoltaic diode performance: short circuit current, representing the current when the diode voltage is zero, and open circuit voltage, representing the voltage when the current is zero. The goal is to deliver generated power to a connected load. The operating point depends on the load resistance. The maximum power point is where the product of voltage and current is maximized. When designing the system, it is essential to determine the optimal load value so that the operating point aligns with the maximum power point, ensuring that the maximum possible power is delivered to the load. Efficiency of a photovoltaic cell is the ratio of electrical power output to incident light power. Efficiency depends on sunlight availability, weather conditions, cell material, and geographic factors such as tilt, orientation, and location. Commercial solar cells typically reach from 8 to 20% efficiency, while experimental technologies can achieve up to 35%. Table 4 lists the efficiency and key parameters of photovoltaic cells made from various materials. Crystalline silicon cells dominate over 90% of the global market. The spectral characteristics of sunlight and artificial light make the choice of photoelectric material critical. Crystalline silicon is preferred for outdoor applications due to high efficiency under strong illumination. Thin film cells made of amorphous silicon and cadmium telluride suit indoor use, as their spectral response matches artificial lighting, though efficiency is lower. Solar energy is abundant and provides the highest power density among common energy harvesting techniques, making photovoltaic cells ideal for outdoor harvesting. However, solar cells are highly dependent on environmental conditions. They generate energy only during daylight. Also, the output power can drop significantly under cloudy skies, or due to heavy shading caused by nearby objects, such as trees or buildings. Furthermore, sunlight angle affects efficiency, with maximum output at normal incidence. Solar tracking can improve performance but increases size, cost, complexity, and energy consumption, so its use must be carefully justified. Thermal energy can be converted into electrical energy using thermoelectric generators, which operate on the Seebeck effect, where a temperature difference across a material generates a voltage proportional to the temperature gradient. A typical thermoelectric generator consists of a P-type and an N-type semiconductor, usually made from doped bismuth telluride, sandwiched between metallized ceramic plates for stability and insulation. The semiconductors are connected electrically in series and thermally in parallel. One end of the thermoelectric generator is kept hot, representing the hot junction, and the other cold, representing the cold junction. The temperature gradient drives diffusion of holes in P-type and electrons in N-type semiconductors, creating an excess of positive charge at the cold end of the P-type semiconductor and an excess of negative charge at the cold end of the N-type semiconductor. This spatial separation of charge carriers results in the generation of an electrical voltage between the cold ends of the P and N-type elements. Connecting an external load, such as a sensor node, allows current to flow as long as the temperature difference is maintained. Materials for thermoelectric generators should have high electrical conductivity and low thermal conductivity to maintain the temperature gradient. A heatsink is often attached to the cold side to dissipate heat, transferred from the hot side to the cold side, helping to preserve the temperature difference across the thermoelectric generator. A major limitation of thermoelectric generators is their low efficiency, typically below 10%. Research focuses on advanced nanomaterials and quantum dots to enhance efficiency. Thermoelectric generators have diverse applications for electrical energy generation. They can exploit the temperature difference between the human body and the environment to power wearable devices such as wristwatches and biomedical sensors for monitoring pulse, blood pressure, and other physiological parameters. Thermoelectric generators can also harvest waste heat from automobile exhausts, industrial chimneys, boilers, and radiators, supplying power to temperature sensors that operate most reliably when overheating risks are highest. Thermoelectric generators can utilize solar energy as an alternative to photovoltaic cells. One side of the thermoelectric generator is exposed to sunlight, which is the hot side, while the opposite side contacts the ground, which is the cold side. Efficiency is improved with a black-painted heatsink, a parabolic concentrator, and a transparent cover to trap heat. Performance depends on environmental conditions such as daylight, cloud cover, and shading. Another approach uses the temperature difference between air and soil, which allows thermoelectric generators to operate day and night, with reversed heat flow direction at night. A heatsink mounted on the upper side of the TEG collects heat from the air, while the lower side of the TEG contacts the ground via a metal rod, transferring subsurface temperature. Weather conditions also influence performance. A key advantage of thermoelectric generators, like photovoltaic cells, is their ability to deliver direct DC output, eliminating the need for rectification. The main limitation is low efficiency, theoretically capped by the Carnot cycle, which depends on the temperature gradient. Small temperature differences yield very low efficiency. For example, a temperature gradient of 10 degrees Celsius gives an efficiency of 3.2%. Even for a large temperature gradient of 100 degrees Celsius, efficiency remains below 20%. Practical thermoelectric generators operate far below this limit, requiring very large temperature gradients to achieve higher efficiency. Kinetic energy arises from motion and vibrations that are widely available in the environment. Typical applications of kinetic energy harvesting include powering sensor nodes using vibrations from machines and industrial equipment, structural vibrations in buildings and bridges, and energy harvested from human and vehicle motion. Examples include transducers integrated into shoe soles for wearable electronics, embedded in floors and high-traffic public spaces, or installed beneath road surfaces to harvest energy from passing vehicles. Three main types of transducers are commonly used to convert kinetic energy into electrical energy: piezoelectric, electromagnetic, and electrostatic generators. Piezoelectric generators convert mechanical deformation into electrical energy through the piezoelectric effect and are typically fabricated from synthetic piezoelectric materials. When a piezoelectric element is stretched or compressed, opposite electric charges appear on its two surfaces, creating a voltage difference, which is collected using thin metal electrodes and fed into an electrical circuit. Piezoelectric materials are anisotropic, meaning their response depends on direction. Two commonly used operating modes are 3-1 mode, where deformation in direction 1 generates voltage in direction 3, and 3-3 mode, where both deformation and voltage occur along direction 3. Most piezoelectric generators are implemented as cantilever beams with a seismic mass attached to the free end. External vibrations cause the mass to oscillate, bending the beam and deforming the piezoelectric layers, which generates a voltage across the electrodes. The piezoelectric generator produces an alternating voltage that must be rectified before it can be used to power sensor nodes. The third figure illustrates a piezoelectric generator connected to a diode rectifier. Electromagnetic generators operate based on Faraday's law of electromagnetic induction, where a time-varying magnetic flux induces a voltage proportional to the rate of change of the flux. An electromagnetic generator consists of a coil and a permanent magnet. Two configurations are possible: a moving coil with a stationary magnet or a moving magnet with a stationary coil. In both cases, the changing magnetic flux through the coil induces an electromotive force, producing a voltage across the coil terminals. When a load is connected, the circuit is closed and current flows. The figure illustrates a generator with a stationary coil and a moving magnet, where the magnet is attached to a seismic mass and oscillates under external vibrations, generating a time-varying magnetic flux in the coil. Electrostatic generators are capacitive devices consisting of two electrodes separated by a dielectric. Their operation is based on external vibrations that cause relative motion between the electrodes, either by changing the electrode distance or the overlapping area, which leads to a variation in capacitance. Since capacitance is the ratio of stored charge to voltage, a change in capacitance results in a change in either charge or voltage. Two types of electrostatic generators exist: constant charge generators, where the charge remains constant during motion, and constant voltage generators, where the voltage is maintained constant. Energy conversion occurs cyclically, with each cycle starting at maximum capacitance, when the electrode spacing is minimal. In both cases, an external voltage source is required to initially polarize the capacitor at the start of each cycle. The operating cycle can be represented using a QV diagram, which includes two key lines: the line containing points A, B, and C, which corresponds to maximal capacitance, and the line containing points A and D, corresponding to minimal capacitance. The operating cycle of a constant charge generator is represented by the contour ABDA in the QV diagram and consists of three phases. Phase 1 is a pre-charge phase, which corresponds to the AB line in the QV diagram. The cycle starts by pre-charging the capacitor using an external voltage source, while the capacitance is at its maximum value, corresponding to the minimum electrode separation. Phase 2 is the phase of electrical energy generation and corresponds to the line BD. The capacitor is switched to an open circuit condition, and the electrode separation is increased by an external mechanical force, causing the capacitance to decrease. Since the charge remains constant, the voltage increases until the maximum electrode separation is reached. This is point D in the diagram. During this electrode separation process, energy is accumulated in the capacitor. Phase 3 is the discharge phase, corresponding to the line DA in the QV diagram. In the final phase of the cycle, the capacitor is connected to a load such as a sensor node, a battery, or a supercapacitor, and delivers all of its stored energy. The net energy gain is equal to the difference between the energy delivered to the load and the energy initially invested in pre-charging the capacitor. The operating cycle of a constant voltage electrostatic generator is represented by the loop ACDA in the QV diagram. Phase 1 is the pre-charging phase, corresponding to line AC. The cycle starts by charging the capacitor to its maximum voltage, where the capacitance is also maximal due to the minimum electrode separation. This is represented by point C. Phase 2 is the phase related to the transfer of energy to the storage element. This phase corresponds to line CD. During this phase, a mechanical force increases the electrode separation while the capacitor is connected to a voltage source, maintaining a constant voltage across it. As the electrodes move apart, the capacitance decreases, causing the charge on the capacitor to decrease by being transferred to a storage element, such as a supercapacitor or battery. This phase continues until the electrodes reach their maximum separation, at which point the capacitance is at its minimum. At point D, after the electrodes have fully separated, the capacitor still retains some charge, representing residual energy. Phase 3 is reset, corresponding to line DA. In this final phase, this remaining charge is also transferred to the storage element, completing the cycle. The generated energy is proportional to the shaded area in the QV diagram. The area corresponding to the constant voltage mode, ACDA, is significantly larger than that of the constant charge mode, ABDA, enabling system efficiencies of up to 80% for constant voltage devices, compared to about 30% for constant charge devices. This performance advantage explains why constant voltage operation dominates current electrostatic energy harvester research. Electrostatic generators can be classified into three fundamental topologies, as illustrated in the figure. The in-plane overlap varying topology converts vibrations into electrical energy by changing the overlapping area between interdigitated electrodes, where one structure is movable and the other is fixed. The in-plane gap-closing topology operates similarly, but electrical energy is generated by variations in the gap distance between the interdigitated electrodes rather than their overlap. The out-of-plane gap-closing topology uses two parallel plate electrodes, where vibrations change the distance between the plates, resulting in electrical energy generation. A kinetic to electrical energy converter can be modeled by the system shown in the first figure, consisting of a seismic mass, a spring, and a damper. This system has a resonant frequency. Let the system be excited by ambient vibrations. These vibrations induce oscillations of the system, and maximum electrical power is generated when the resonant frequency matches the excitation frequency. A key limitation of such converters is their narrow operating bandwidth, typically only a few hertz, which restricts efficient operation to cases where the excitation frequency closely matches the resonant frequency of the system, or when their difference is limited to just a few hertz. Therefore, a critical design requirement is to tune the converter's resonant frequency to the dominant vibration frequency. When ambient vibrations have a broadband frequency spectrum, the operating bandwidth of the converter must be widened. This can be achieved either by using springs with a nonlinear stiffness coefficient or by employing multiple oscillatory subsystems with different resonant frequencies so that the overall bandwidth becomes the combined bandwidth of all subsystems. Radio frequency electromagnetic waves represent an important energy source for energy harvesting. Due to the widespread use of wireless communication technologies, RF energy is now ubiquitous in the environment, originating from sources such as radio and television transmitters, mobile communication base stations, mobile phones, radar systems, Wi-Fi networks, microwave ovens, and other RF emitters. An RF energy harvester consists of an antenna, which captures ambient RF radiation and generates an AC voltage. Since AC voltage cannot directly power sensor nodes or charge energy storage elements, it is converted into DC using a rectifier. To ensure maximum power transfer, an impedance matching network is placed between the antenna and the rectifier. Antennas must satisfy requirements related to operating frequency bandwidth, radiation pattern, polarization, and gain. Common antenna types include patch, dipole, microstrip, planar, and uniplanar antennas, whose physical geometry significantly affects performance. Examples include hexagonal, Archimedean, and square spiral antennas. Rectifiers can be implemented using various circuit topologies, most commonly based on diodes, which allow current to flow in only one direction. Schottky diodes are often preferred due to their low forward voltage drop and fast switching speed. In practice, voltage doubler and voltage multiplier circuits are widely used. Besides rectification, they boost the DC output voltage, making them particularly suitable for low input voltage applications. Impedance matching circuits are typically built using reactive components like inductors and capacitors, as illustrated in the figure. The main challenge in RF energy harvesting is the very low signal level. For a practical implementation, the harvester must either be placed close to the radiation source or use a large antenna, often much bigger than the sensor node itself. Wind generators convert wind energy into electrical energy. While large-scale wind turbines have been deployed for decades, sensor nodes rely on small-scale generators only a few centimeters in size. A wind generator consists of a turbine with rotating blades, which drives a shaft connected to a permanent magnet with coils positioned nearby. As the magnet rotates, a time-varying electromagnetic field induces voltage in the coils via Faraday's law. Wind energy is intermittent and variable, fluctuating annually, seasonally, daily, and even within a day. Wind speed also depends strongly on height above ground, being much lower near the surface due to obstacles like vegetation and buildings. This limits the performance of small-scale wind generators, which are usually installed at low elevations. Increasing height improves wind speed, benefiting large-scale turbines on tall towers. Small-scale wind generators typically achieve efficiencies below 10%, much lower than large-scale turbines, which can reach about 50% efficiency. The rise of wearable electronics and implantable sensors has created a demand for reliable, long-term, safe, and maintenance-free power sources. Conventional batteries have limited lifetimes and often require recharging or replacement, which is inconvenient for wearables and almost impossible for implantable devices. This has driven research into harvesting biological energy naturally available in the human body. The human body continuously generates energy in various forms. Body heat energy can be used for powering low-power wearables like fitness trackers and health monitoring patches. Chemical energy from glucose is especially suitable for powering implantable devices like pacemakers and continuous glucose monitors. Mechanical energy of movements such as walking, running, breathing, and joint motion can be converted into electrical energy by piezoelectric, triboelectric, and electromagnetic harvesters. Examples include piezoelectric elements in shoes or triboelectric generators in textiles. Blood flow energy causes vessel wall deformation, which can be harvested using miniature electromagnetic or piezoelectric generators to power cardiovascular sensors. Hybrid approaches that combine multiple biological sources are being explored to ensure consistent energy availability, allowing devices to generate power under varying activity levels and environmental conditions. Within this tutorial, we covered energy harvesting systems, which collect ambient energy such as sunlight, wind, heat, mechanical vibrations, electromagnetic waves, and biological energy, and convert it into micro-scale electrical power for sensor nodes, edge devices, and wearable electronics. We explored the architecture of energy harvesting systems, including energy storage elements like rechargeable batteries and supercapacitors, and their key characteristics. We also reviewed the main types of energy harvesters, such as photovoltaic, thermoelectric, mechanical, RF, wind, and biological harvesters. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.